Okay, so we're back with examples of finding the derivative of integrals where the boundaries are a little bit more interesting. You notice the first thing that this boundary is a 2x, not an x. Recall from the last video that the derivative of an integral simply, they undo each other, they're inverse operations, and then you plug this boundary in for t. So we got 6 times 2x. Now, because we're plugging in a 2x and we are technically taking a derivative, chain rule would then say that we have to multiply by the derivative of the inside being 2x. So in addition to plugging in the 2x, we actually have to multiply by its derivative, which is 2. And in the end, we get 24x. So the only thing new here is that whenever the boundary is anything other than x, you must multiply by the derivative of that boundary. Here's another example. The derivative of an integral, and this time we're using the function 2t squared plus 3t, and the boundary is 5x squared. We're going to plug that boundary into t here, and we're going to plug it into t here. So we will end up with 2 times 5x squared. That's from the boundary, and then we square it again because the t was squared to begin with, plus 3, 5x squared. Okay, since we've plugged that all in, that boundary, we also have to keep in mind that we have to multiply the entire expression by 10x. That would be the derivative of this. You could have multiplied each term by 10x or just multiply it all at the end by 10x. Let's go ahead and simplify a little bit. This will be 25x squared. So I'm going to go ahead and pause and then do my simplification because these numbers are going to get a little bit big. Okay, so I'm back. I went ahead and squared the 5x squared, and notice the 5 also got squared, and that should be x to the 4th. But then we're going to also multiply it by 2, and so we get 1250 as a result of doing that. And then this term wasn't squared, so it's just 3 times 5, and here we are. And now I'm just going to multiply it by 10, and that adds a 0 to every coefficient. So x to the 4th plus 150. And I want to go ahead and say this is going to end up being 5th power because of the x that we're multiplying. And then that's it. So again, you plug in your boundary and multiply by the derivative of that boundary and you're set. We're going to do one more, and then we're going to summarize what we've learned so far in terms of fundamental theorem of calculus. And if you need more examples, I'm going to make a third video with additional examples, but they're basically repeating the same process, so if you understand and you're comfortable, you don't need to watch them. But if you would like extra help or extra guidance, then you can do it that way as well. Derivative of an integral, they cancel. Now you're going to see that this one has a boundary that is an x squared, contains an x term, and the other boundary also contains an x. When this happens, you can't just ignore that bottom boundary anymore because it's no longer a constant, it's an actual function, 3x, x squared top boundary. So what's going to happen is the following. You're going to plug in the top boundary into t, and this looks scary, but remember, you're just plugging in because you're taking the derivative of an integral, so there's nothing to be afraid of here. 1 over 2 plus e to the x squared. That's the first part. But you need to go ahead and multiply that by the derivative of that boundary, which is 2x. Okay? And now since the bottom boundary has an x in it, we're going to subtract and go ahead and plug that guy. It's always subtract. And that goes back to how we evaluate an integral. You know, the antiderivative of f minus the antiderivative of b minus the antiderivative of a. So that minus is going to come from that concept. So okay, putting this guy in would be 2 plus e to the 3x, excuse me. And then again, you also have to multiply by the derivative of the inside, which is 3. And so just making this look a little bit prettier, it would be 2x over 2 plus e to the x squared minus 3 over 2 plus e to the 3x. And that's it. So if your bottom boundary is a function of x as well, make sure you plug it in, use subtraction in between those two boundaries, and make sure you multiply by the derivative of each boundary. Last thing is that I want to just go ahead and summarize what we've learned so far. Fundamental theorem of calculus part 1 and 2. Part 2, we started with that one. It says that the area under the curve is the antiderivative of that curve, and it actually allows you to evaluate integrals with antiderivatives using this. Okay, so when we say FTOC 2, this is what I'm talking about. FTOC 1 is what I've gone over in these more recent videos. It connects derivatives and integrals as inverse operations. They undo each other. It says that every derivative has an integral and every integral has a derivative. And then this is the official notation. If you take the derivative of an integral, you simply end up with the starting function that was inside that integral with x plugged in. And that's your summary. Alright, so you can go ahead and work on your assignment, or you can watch the third video which has more examples for your guidance. Shout out to Brianda Lopez because she said that she wanted me to give her a shout out, and she says she's going to like me on Facebook, follow me on Twitter, and something about YouTube. I don't know. I'm working on it.